today, by way of announcement, we have the midterm study guide and the midterm posted. Spoiler alert, they're exactly the same. And so I've mentioned this before, but this is something I added to the class, which hopefully you won't be too mad at me for, because my purpose in adding it to the class was because I want to, I think it helps to have some sort of concrete something to take away from this class. We cover a lot of content in the slides, and I think it's helpful to have something to kind of like narrow down the core concepts to. And these are the concepts that will come up in interview questions and things like that. So the purpose of this midterm is to, try to give you, give you an idea of like what the most important things in this course are to prepare you for future jobs in this field. So the midterm is posted on Learning Suite. Feel free to pull it up. We're going to be going through it question by question today. After we do a little bit of review on diffusion models and the lab due this Saturday. Also, big shout out to Benjamin Havens, who helped push the diffusion lab through this Saturday. I apologize for kind of some of the crazy TA hour situations. So if I was the one, I claim full responsibility. I was the one who told Ben to cancel his office hours Friday so that he could finish this diffusion lab for you guys. So if you weren't able to finish the reinforcement learning lab on last week because you needed TA help, just message me on Slack, and you can get the TA help today, turn it in late, and I will waive the late penalty if that was your issue. One other thing, it sounds like the late submission was closed for the reinforcement learning lab. I reopened that, so you should be able to submit it now. Okay. Any questions on all of those announcements? Yeah, Jacob. Yeah, well, what was that? So the weekend counts as one day. So submitting it on Sunday is the same as submitting it on Monday, because it's due Saturday night, right? And so, it'll still have the late penalty taken off. But if your issue was getting to the TAs, then feel free to message me on Slack. Okay. Stable diffusion. By show of hands, who had a chance to watch the recorded lecture from Friday? Okay. Who did not get a chance to see that yet? Okay. Definitely make sure you watch that, because that is the lab that is due this Saturday. That is very important. Today we're going to start off with a review, not of diffusion in general, but of the stable diffusion architecture that you will be working with in the lab. So this will assume that you watched the video lecture and you have a basic knowledge of diffusion models. So this is the diffusion model architecture. I'd like to invite you to turn to the person next to you and see if you can explain the three different aspects of this diagram: this epsilon and D, the red box, the green box in the middle, and the white box on the right. Right. So yeah, in our diffusion model, can someone explain to me what this red box is? So just a hint, this red box is unique to the stable diffusion model. So this is not something that all diffusion models, but it's specific to this architecture. Oh, okay. Any thoughts? Yeah, Jared? Yes, exactly. So X represents image space. So X is the original image, and then X tilde is the reconstructed image from our noise vector Z. Yep. And so this architecture kind of loops around from the top left to right, and then on the bottom right to left. Yeah. And then inside this red box, we have an encoder and a decoder. And this is what makes stable diffusion different from other models. So stable diffusion we can run in Colab. Other diffusion models we cannot. And the reason for that is because normal diffusion models work in pixel space. So you have a full, if your images are 512 by 512, you have a full 512 by 512 sized activation map at each step, which is pretty memory intensive. The stable diffusion basically downsamples and then upsamples that image into a latent space Z. And that's why we're going to call it a latent diffusion model. And so all of the diffusion happens in latent space. So yeah, we encode the image into latent space. Diffusion happens in latent space. And then we decode from latent space back into an image. Yeah, Drake. Good question. So the question is whether Z is a vector or whether it's a grid. It depends on what your inputs X are. So in this case, this model is for images, and so X is an image, and so it has spatial dimensions, and so Z will have spatial dimensions. Yeah, if this were some other modality like text or something, it would be a one-dimensional vector. But yeah, so Z has two spatial dimensions. Good question. All right, any questions on the encoder decoder and how latent diffusion using diffusion in latent space is helpful for us? Okay, so then in this green box we have the diffusion process. So as a reminder, in diffusion we have forward diffusion and reverse diffusion. Forward diffusion takes an image and turns it into a complete noise vector. So a vector sampled from a standard normal distribution. In this case, when we have spatial dimensions, it's a standard normal sample for each pixel. Yeah, Jaden. Yeah, so it's not a random. So if you're talking about like random choice, like the method in PyTorch or NumPy. Yes, it is a sample from a random normal distribution. Yep. And in this case, it will be a grid of numbers because ZT is a grid. And then so the forward diffusion process is given just by gradually adding more and more noise from samples from a Gaussian distribution. The reverse diffusion process is learned. And so basically the whole idea behind diffusion models is that we want to train a neural network to match the forward diffusion process with a learned reverse diffusion process. Okay, and so the way that we're going to do that is we are going to train, then the architecture of what that looks like is going to be a U-net. So you've seen U-nets before. They map pixels to pixels, spatial dimensions to spatial dimensions, and we will just apply that ZT times to gradually take a noise vector and remove at each time step t, we will remove more and more noise to get back to an image which is a sample from our image distribution as opposed to the normal distribution. Any questions on this latent space and the diffusion process that happens in it? Yeah, Dane. The noise applied to each layer is you're saying that it's the same from image to image, it's different for each image. Mm-hmm. Yeah. Yeah, Max. Okay, yeah. So you're wondering about this switch at the bottom right, and this this little loop on the left side here, where we have like a mini unit. It's repeating with the same weights every time. Mm-hmm. Yep. And so this is just an abbreviation to say that we're going to apply this unit t-1 times till we get back to a sample z0, which we will transfer into x0. Yeah, I'm actually not 100%, but I'm pretty sure it's for conditioning. So it determines whether, yeah, to be honest, I'm actually not 100% on that, but I think it is possibly to turn on and off conditioning. So that conditioning is something that we haven't talked about yet. So let's talk about that. So this diffusion architecture, the red box on the left and the green box in the middle, it applies to unconditional sample generation. However, we can also train our model to condition, which means that we want to generate images based on some other thing that we want to associate with those images. So that could be, we have a segmentation map of a street view where you have cars, road, trees, etc. And we want to generate images to fill in that segmentation map. So we could condition on an image, or we could condition on text, like we did at the beginning of this semester, where we had Yoda or Luke Skywalker riding on Yoda's shoulders. And so to do that, we will take a pre-trained network that will extract features from text, images, semantic map, whatever, and we will call that feature vector tau theta. And then then the question is, how do we incorporate tau theta in our denoising diffusion process? If you just to ask you guys, like, if you were to do this from first principles, how much, and you wanted to condition this unit on some other information, how would you do it? You wanted to incorporate text into your generation process. Yeah, Tim, what do you think? Totally, yeah. So you could just concatenate tau to your z vector. We'd have to think exactly how we wanted to do that, because one is spatial and one is not. But I'm sure we could figure out a way to do that. That could be a totally valid way to do it. Yeah. So concatenation. You might consider adding, which we've seen is very similar to concatenation. In this case, this is kind of interesting. They are going to do, the authors of this paper do cross attention between our diffusion model and this conditioning information. And so the way that they do that is our diffusion model provides the queries, and then tau theta acts as the keys and values. And that allows the unit to basically incorporate as much or as little information of tau theta in each spatial dimension of its generation as it likes. Okay, so any questions on that cross attention for conditioning that Stable Diffusion uses? Yeah, Jaden. Yeah, so queries, keys, and values are 3 different transformations of our inputs that that basically can be interpreted in 3 different ways for how we want to update our embeddings. So, and probably the key thing the most important thing to remember or to think about as far as Q, K, and V in this context is that Q determines the shape of your output. And so because of that, we're going to use ZT as our query. Q you can think of as like the embeddings that we are updating. And so, yeah, because we want to update ZT, that's going to act as our Q. And then K will tell us how each ZT relates to tau. And V is basically just a transformation of tau. And so we'll take a linear combination of tau as an update for our ZT. But yeah, ZT is our Q, and that determines our the size of our output of our cross attention. Yeah. Totally, yeah. X is an image. Good question. Yeah. So the question is are we just trying to make X tilde match as close as possible to X? Kind of. So that would be like a reconstruction loss type of thing. What we're doing is we're trying to match at each step of the diffusion process. So rather than just trying to make X match X tilde, we're trying to make Z1 in the forward diffusion match Z1 in the reverse diffusion, and Z2 in the forward diffusion match Z2 in the backward diffusion, and so on. So we want it to match at every step, and that's why it's kind of different from a reconstruction loss. Yeah, so the question is, what kinds of problems is this applied to? So the main problem that people have used it for is generating images, like yeah, photorealistic images with conditioning. In my field, actually, people have applied this to generating molecular conformers. So you take as input a graph, and you try to predict coordinates of because molecules can be kind of twisty in space. And so that kind of process of like twisting rotating around the bonds of a molecule can be thought of as kind of a diffusion process, a physical diffusion process. And so these diffusion models have actually been used quite effectively on several molecular modeling problems as well in my field. So kind of cool. All right, Craig. So to predict, are we sampling from Z of T? Yes. Yep. And if we want to condition, then we're also taking a tau sub theta that comes from our prompt. And then, yep, then just following that reverse diffusion process to generate a sample. Good question. All right. Yeah, Dane. Why do we generate noise at subsequent layers instead of providing a random vector? So are you talking about training time? So the reason why we don't assign a random vector to ZT is because basically our training objective is incremental. And so we want to have the difference between like Z1 and Z2. That's going to be our training signal. And so like in a way, we are just throwing random noise in over and over and over, but it needs to be random noise applied to an input image so that we can learn the backward process of removing that noise at each step. I'm not sure if that answers your question. Okay. All right, so just a couple more concepts for the lab. So yeah, this is the conditioning via cross-attention, where you remember that Q is provided by Z, and then our keys and values are information from tau that we're incorporating into Z. One other note on this, because Z has spatial dimensions, when we perform cross-attention, we flatten all of those spatial dimensions into a single vector. Okay, this is probably the most important part to understand for the lab. Most of the lab for you is just annotating and explaining things that are happening, but you will actually implement this part of the lab. So I think it was Craig asked a question about sampling from the model, and I told you a half-truth. I told you that the way that you sample from the model is you take a Z vector and you run it through our denoising model T times. Well, it turns out that there's this paper called DDIM, which shows that you can take a trained model and you can sample from it in fewer steps than you used for training, which is kind of an amazing theoretical result. And this is how you do it. It's by, actually, this is not the equation. This is like a different version of the equation that you're going to implement in the lab. But the equation that you will implement in the lab is in the paper, and you'll have it. You'll have access to it. It's equation 12 from the DDIM paper. So basically, the result is that we can take xt, which is a sample at any time step, and generate a sample at any other time step, t minus delta t, instead of just t minus 1. And we do that by varying the weight that we put on our denoising prediction. And so, yeah, you can see that the things that are different in this equation versus the normal diffusion update are the delta t's instead of -1. And so if you, basically if you change this alpha parameter, which is the noise parameter, you can change how much, you can change which step you are denoising to. And the effects of that are pretty powerful. So these are images from a model trained with t equals 1,000 training steps, diffusion steps during training. And tau is the number of steps used during inference for sampling. And so they tried tau equals 100 and tau equals 10. And you can see that tau equals 10 is maybe a little blurrier than tau equals 100. But both of these are, I mean, tau equals 100 is a 10x reduction. Tau equals 10 is a 100 times reduction in sampling speed. So this DDIM sampling is a pretty powerful thing, and that's why we'd like you to understand how to implement it. Yeah, and so just to go back to this equation, this equation has a lot of terms in it, but should be fairly easy to understand. So we start with an xt, that's just an image at the current time step. And then we're going to add some denoising factor that we get from our model. And that will give us our updated image x. And then basically we can choose our tau, our number of inference steps. And from that number of inference steps, we can come up with our delta t. So question, so if we have t equals 1,000 during training, and we want tau equals 10 during inference, what will be our delta t? Yeah? Yep. Exactly. Yep. That is exactly right. Yeah. So basically, to get your delta t, you just take the number of training steps divided by your number of inference steps. And that's probably like the hardest part of that section of the lab, and we just gave you the answer to it. So just to review, yeah, you get delta t by dividing your number of trained samples by your number of inference samples, tau. Okay, any questions on DDIM sampling? Yeah. It does not need to be constant. Yeah, so it could be really interesting to experiment. Like, is it more important to have delta t to be small at the beginning or at the end of that diffusion process? That would be an interesting question to ask. Totally. Good. Yep. Yep. During training, we're denoising at 1,000 different steps. Yeah. Correct. Only during inference do you use tau, and the reason for that is because during training we basically sample a random time step at each training iteration, and so it doesn't really cost us a whole lot to have a larger capital T because we're just sampling from that anyways during training. All right. Okay, so that is the diffusion lab. Okay, so now we are going to take a look at midterm. Does anyone know how to collapse this top bar? That works. Okay. All right, so this is the midterm. So I'd like to, because we have about 20 minutes left, I'd like to hear, I'm not sure we'll be able to get through all of the questions, but I'd like to invite you to pull up the midterm study guide on from Learning Suite and let me know which questions you feel like you'd like a review on, and we will go into them. So yeah, go ahead. The 14 and 2. Let's see. Okay, so oh, you're right. Does anyone know the answer to 14? C is the correct answer for 14. Yeah. For sure. Yeah, I will make a note of that. Number 2. Yeah. So that's a matching question, and so the matching questions just their answer is separated by a dash. Yep. Good question. Okay. Yeah. Just raise your hand if there's a question you'd like to go over, and I'll list them on the board, and then we'll see how many of them we can get through. Yeah, Brett. Let's see. You're totally right. Okay, yeah, sorry about that. I will update that. Thanks for that catch. All right. Yeah. So the correct answer for 1 should be A, 6 dot products, not B, 10 dot products. Yeah. All right, yeah, what questions would you like to go over? Jacob? It's multiple choice with a couple of matching questions. Yep. Okay. Yeah. Totally. Yeah. Okay, 8 and 9. I mean, if you feel confident about these, I can just let you out early, but I'm guessing there are some of these that you should have questions on. Yeah, Max. Yes. Absolutely. Okay. Yeah. Yep. Anything else? Yeah, Brett. What an inception score is, yes. Dane, did you have one? One, okay. All right. Well, yeah, let's go into those. And I'm actually going to add one myself that I feel like I could have explained much better, but which, yeah, this is one of the most common questions that you get asked on in interviews, and one of the harder things to understand. So that's the bias variance trade-off. Okay, let's go right into it then. Okay, so the bias variance trade-off. So in deep learning or in prediction problems in general, you can consider a problem where you want to predict y from you want to learn a function between y and x. And that function is given to us implicitly through a data set. And the relationship between x and y is given by y equals f of x plus epsilon, where epsilon is some amount of noise that is inherent to our data set and which which is just something that we will never be able to learn because it's noise. So our estimator for y will be given by f hat, which is the true function plus the noise. And so we're going to look at the mean squared error loss function as an example of how this bias variance trade-off breaks down between basically how bias and variance contribute to our error in different ways. So the mean squared error is given by the expected value across our data set of the squared error between our labels y and our predictions f hat. Any questions on that first line? And so, oh, and actually, sorry, it's y that is composed of the true function plus some epsilon noise. And so this is what our mean squared error is, and we're going to basically FOIL out this, this function and then show how it reduces into bias and variance. So actually, we're not going to go through this proof, but let's skip down to this line right here. So just trust me that all of these lines are correct, and you can go verify it on Wikipedia later if you like. But what we end up with is we get the difference between f, the true function, and the expected value of our predictor f hat. And so f minus the expectation of f hat is known as bias. That is the definition of bias. So it's the difference between the true function and the expected value of our predicting function. Okay, and then we have the expectation of epsilon squared, which is irreducible error, and then the expectation over the expectation of f hat minus f hat squared. So this term right here on the right is the variance of our predictor f hat. And so then this ends up reducing to the variance of f hat plus the variance of our noise, sigma squared, plus the squared bias of our model. And so basically our mean squared error will be composed of a bias term, a variance term, and a noise term. Any questions on that? Okay, so we can then introduce regularization to this mean squared error. And that looks like this. So on the left here, x theta minus b is our mean squared error. And on the right, we're going to add a penalty on the size of our parameters, theta. And so we're going to have some lambda weighting term times the squared value of theta. And we're not going to go through the derivation, but when you do the same mean squared error decomposition in terms of bias and variance, you end up with something that looks like this, where lambda is that scaling term for regularization, and sigma squared is your irreducible error. And so looking at this, of these three terms, bias, variance, and sigma, what happens to the bias as we increase lambda? And I'll tell you that actually, I'll just tell you this. Sorry, I don't want to leave you guessing. So as we increase lambda, this inside term is going to be negative, and so that cancels out with the negative. And so as we increase lambda, our bias will increase relative to our variance. As we decrease lambda, our bias will increase, and as we decrease lambda, our bias will decrease, but our variance will increase. And so here we look at three different values of lambda, and this is fitting a polynomial, but you could think of these as like, so on the x-axis is the degree of the polynomial or the complexity of the model, and on the y-axis is the error. So that error we've decomposed into the total error, the mean squared error, the bias squared, which is this orange, and the variance which is green, and the irreducible error, which was just the noise, and that's always constant. So that's the red line. So for lambda equals 0, no regularization, you can see that as we increase the degree of the polynomial to fit our data, our bias drops off. And you can think of that as basically our polynomial traces through all of the data points. And but our variance begins to increase. And so the optimal location for minimizing the mean squared error is a trade-off between bias and variance. If we scale up our regularization weight lambda a little bit, we can see that we basically have no variance in our model anymore. And the bias drops off just a little bit. And so basically, no matter how high our polynomial fit is, our mean squared error doesn't increase. So this seems to be a pretty good choice of lambda for regularization. However, if we increase lambda to 0.5 and look at this bias variance decomposition, we have almost no variance, but our bias becomes so high, basically because we're no longer tracing anything close to our points. And so our mean squared error increases. So I just wanted to give you that as hopefully a more thorough explanation of the bias variance trade-off. Any questions on that? Yeah. I can post it on Learning Suite. Yeah. This is for ridge regression. Yeah. Okay. So next, we're going to look at questions 4 through 6, which also relate to regularization. Okay. So does anyone remember what dropout is? Yeah, Joseph? Exactly, yeah. So dropout is when during training we set certain activations to 0. Yeah, and so we didn't look at the derivation of this in class, but that is turns out that is equivalent to L2 or ridge regression, which is also known as the squared error penalty on. It's a penalty on the squared value of our model weights. L1 regularization is a penalty on the absolute value of our weights. So you can think of L2 regularization penalizes maximum or very large values much more than L1 regularization does. Shakeout it is another regularization technique, and actually off the top of my head I don't remember, but I'm pretty sure it's where you assign random labels to a certain percentage of your weights. So it's pretty similar to dropout, except you're using random labels, and that's equivalent to a combination of L1 and L2 regression. Then as far as number 6, does anyone remember why L1 regression is sparsity inducing? Yeah, you want to take a shot? Yeah, exactly. So the one norm drives parameters to 0. And the reason for that is because the one norm looks like an inverted pyramid. And so when you add that inverted pyramid penalty to your normal loss function, you end up basically with these sharp valleys. And so along the places where your parameters are 0. Yeah, and so that's why it leads to those parameters being set to 0. I saw a couple of questions. Yeah. That's what it is. Yes, thanks for looking that up. Yeah, so shakeout is randomly enhancing or negating nodes in your network. Yeah, thanks for that. Sophie. Good question. Yeah, so that's kind of a confusing thing. So it is not, so dropout is kind of like making your network sparse during training, but it turns out that when you take the trained network, so first of all, we're setting activations to 0, not weights to 0 during dropout, and it turns out that like the theoretical properties are more similar to L2 regularization than to L1. And so you actually don't end up inducing a lot of sparsity with dropout. So there's a paper that shows that dropout is theoretically equivalent to L2 regression and has all of the same properties of like not inducing sparsity and things like that. Yeah. Yeah, okay, Matthew. Sparsity is where weights of our neural network are set to 0. Yeah. Okay, 8 and 9. Yeah, we will go over the rest of these questions next time. 8 and 9, so those are pretty simple though. So skip gram negative sampling. You remember we are taking a window around a word. So if we have the sentence, my cat eats fish. We're going to take the word eats and we're going to take the words cats and fish on either side of it. And we want the embedding of cats or of eats to match the embedding of cats and fish. And so the positive sampling of part of that algorithm is where we're saying that we want eats to match we want to maximize the cosine similarity of the eats vector with the cats plus fish vector. The negative sampling part of the algorithm is where we take random words like London and soccer, and we say we want to minimize the similarity of eats with the summed embeddings of London and soccer. Does that make sense for negative sampling versus positive sampling? Okay. All right. We will continue this on Wednesday.